Hello, my name is Steve McBride. I'm the Senior High-Speed Machining Specialist here at OSG, and I want to thank you for taking the time to take a look at this presentation. This is on a demo part we did. We cut this out of Stavax material, and I'll be covering some bullets on advantages and some of the disadvantages when you consider 5-axis machining on some of your parts. Here, we're just going to talk about, like I said, some of the challenges and rewards of 5-axis machining. These are all considerations that you have to make within your own shop when you're looking at a part to determine whether you want to go 5-axis or not. Seems like a great idea, and sometimes it's advantageous, and sometimes it's actually you got to have a 5-axis to get to that part, or you've got to rotate your part to get it in a different attitude to even be able to cut it. So we're going to cover some of those today. So why use a 5-axis for your machining applications? What we're looking at in the advantages area is shorter length to diameter ratios. Because we can tip the part around, change the attitude, that gets us a lot closer to the part without extending tools out like you'd have to do in just a vertical machine. So as shown over here, you'll have better tool holder clearances as well. Again, tipping the attitude of the part will allow you to use different tool holders that aren't so cleared out, so you'll have a little bit better on tool holder clearances. Your cutting tools can also be positioned off dead center, which is, in a vertical, what happens is a lot of times you're using the dead center of the tool, which you got zero surface footage, so it allows you to get those tools positioned off dead center, and you get a heck of a lot better finish, and your tools last a lot longer also. Further undercuts can be machined in one setting just by tipping the part around because you got a 5-axis machine. So that's some of the bullets and advantages of going to a 5-axis machining. Some of the disadvantages, and the first one comes to mind, is the rotary axis. The rotary axis that allows you to tip this part around also typically will slow you down. Depends on the equipment that you're using. There are some out there that are pretty quick, but typically the rotary axis will be your slowest axis, and so that becomes the boss, and therefore you'll have the slowest feed rate that you have to consider for that, and a lot of times it just slows your feed rates down below where you could say run a tool. So you're going to bring your surface footage down, your feed rates come down because of the rotating axis and so on. So the slowest feed rate is going to be the boss. Also, it's typical too for a 5-axis when you think about actually machining in 5-axis. Most people will start with a 3+2, which is your 3 axes, X, Y, and Z, like a vertical, and then they'll tip the part, put it on either a fixture or just one rotating trunnion or a rotation around where you can rotate your part around, and that'll give you a 3+1, 3+2 would be 2 rotary axes that you could position. So 3+2 is actually your 3 simultaneous axes that you can do on the machine, X, Y, and Z, and then it would be +1 or +2, which would add 2 other axes to it. So it's a little bit harder to program and to keep from. The last thing anybody wants to do is wreck your machine. So it's a little bit harder to program. Therefore, the programmer is going to have to be a little bit higher caliber to be able to program a 5-axis machine as compared to just a 3-axis. And then 5-axis machines, again, they're not all the same, but 5-axis machining may not be as rigid as a 3-axis vertical machining center. They may have boxways, and there's other things to consider. They might be a little bit slower in their feed rates and stuff like that. So, but it may not be as rigid. So that's another what we call a disadvantage. This is, like I said, we were machining a tail light, and it was made out of Stavax material, and the reason we went with Stavax was to get real bright, high surface finishes on this, and it worked out pretty well. And it's a premium stainless steel. It's ideal for transparency, and there are some U.S. guidelines. It depends on the manufacturer and the company that you're working for to produce these molds. Sometimes these U.S. guidelines can prevent polishing on the lens, and what they don't want to do is distort the surface. They want it to be as close to geometry as what they can get in order to get the best reflective qualities of a lens. And so that can be a little bit of a drawback there on those preventing polishing, and you have to have a real bright finish right off the machine. Now in this slide, I'm just trying to bring it to light. You know, just because it's designed with a sharp corner in this area that originally was dead sharp, and we asked them if we could change in the design area, if we could change the design a little bit to add at least a 0.5 millimeter so we could get in there and mill that out, as opposed to stopping the milling process and then going to the EDM machine, electrical discharge machining, and having to burn that sharp corner. And in our case, they allowed us to add a 0.5 millimeter radius to these sharp corners that were around this little pillow pocket on this lens mold. And all this is showing is the original. We had 2 millimeter going around here, and this is all part of our evaluation process. So the idea here is if you don't ask, the answer is always going to be make it like the print. So, but you can ask, and you never know. All right, this is just showing, and you can see the highlighted areas right in here in the black, and then over here you got a little black areas, some undercuts in here, undercuts here, and undercuts in themselves aren't that bad, but when they become at an attitude that you can't get from a 3 axis machine, you know, a straight vertical machine, then you need to either tip the part, change the attitude so you can get into these areas. It's obvious you never come in here with a vertical, you won't make it. So you got to tip that, or you got to have a 5-axis machine. It's one or the other, or you have to machine it some other way. So it's just one of the challenges that you kind of run into that makes you want to think about just putting it on a 5-axis instead of a vertical machining center. All right, what we did on our block prepping and roughing on this part, we wanted to have a good straight edge to start with and a good flat bottom that we could use to for strength more than anything, because we didn't have a lot of good mounting ways to grab this part when we started the demo. So what we did is, instead of putting this in a 5-axis, knowing that we wanted to flip this part over and then start roughing on it, we wanted a little bit more robust machine. And so what we use, these are Microns, and GF Machining Solutions allowed us to use their equipment in their showroom. And so what we used was a machine that was a little more robust, a little bit slower, didn't have 5 axes, and but we were able to prep the bottom, flip it over, and then start roughing on this part. And that's just what we chose to do to get started, as opposed to just throwing it on a 5-axis machining center. All right, step 1, and what I'm referring to there on step 1, we use something we call at OSG a 7-step process. And it's just a 7-level set of processes that we use on almost any cavity core that we run, at least demo-wise, to make a part that looks like jewelry when we're finished. And so step 1, right off the bat, we flip it over after we prep the part, and step 1 is called Z-level roughing. Some CAD systems or CAM systems call it fixed axes, and they may have some other names for it, but it's basically, if you think of like slices of cheese, we're just slicing this in the Z level, step by step by step, and we machine everything on that area that needs to be removed, and then we step down and cut the next area and repeat that all the way down till we get down to the finished part. So Z-level roughing is what we use as step one, and that's why I'm referring to step one. I'm not going to go through all 7 steps, by the way, but you can call me anytime. All right, this is just a little tip, just to bring it to mind. Sometimes they don't think about it. Programmers may not turn a toggle here, and they may have the option where they can just add a radius in this area. And so if you look at this, it's pretty sharp. So what's going to happen as you're Z-leveling down, every time it comes around, this is the green is the toolpath. In these corners, it's just going to hit it like that, and it's going to go around, and then it's going to step over and cut this and hit it there, and so on and so forth, and then repeat that every level down on a Z-level roughing routine, which is, this is the roughing 1 pattern that you're looking at. Now, if you notice, what we did is we put a little radius in here, and it can be by percentage. You can put a little 10% of the cutting diameter. So if you used a 1-inch tool, it'd be like a 0.1 hundredths of an inch in radius in there. So what that does is every time it takes a cutting path here, it doesn't ram in the corner. It actually cuts around the corner. That does 2 things. Because you're not engaging the cutter as much, you get better tool life that way. It doesn't engage, you know, and get a lot of vibration and stuff like that. And it's also faster and smoother because your high-speed look-ahead controls look ahead, and they can zip around here because it's not going in a sharp corner. So this is the tool path that you want to use when you're doing high-speed machining. Okay, stock models for success in high-speed machining. It's very important. So question is, do you have stock model capability? You either have it or you don't. I think most systems out there today have that capability, or you might have it and not be using it. Can't imagine not using it if you got it, but here's 3 things that'll make your life easier with a stock model. It only machines where material remains. You have minimal air time because of that. So it's not hopping all over here. Let's say you're going to go back in here after you've roughed this thing out. You're going to go in with a smaller tool. And without stock model, it doesn't have any idea what stock is left. So it's going to be doing a lot of air cuts around here until it gets down to where there is material, because it doesn't know where the material is from the last tool that you used. So it makes your life a lot easier if you got it, because then it knows you're cutting that stock model that was left from the first roughing tool, and you only go into the areas where it knows it has material that has to be removed. So basically you'll have minimum air time, and it cuts a lot out of your air time. It'll also do interference checking between your tool and your holder, and depending on how much information you put in there, it can even do it on all your rotating axes and all the pieces of that rotating axis. You know, the tables, the fixtures, all that stuff. It can be checked for interference, which we all know, if you can check and it shows you interference, then you're not going to run that program. You're going to have to change something, hang the tool out further, change something, use a different tool holder, so that you don't have those bumps or crashes that none of us want to see. So it gives you a great visual of the process that you just did, and it also allows you to see how your next tool in line is going to cut and react, how much air time you're going to have jumping around to different places to get stock out of a part. You might see it doing something in these little corners here that you don't like, and just eliminate that push node. So it's a great visual to see what each part looks like after each separate tool. All right, step 2, we already did step 1, that's Z-level roughing. And now our very next step of the 7-step process would be step 2. And what we do is we go in here and we remove the corners, remachine the corners is what we call it. And we go in here and go in where the roughing tool left material in the corners and fillets around this part, and we call that remachining the corners. We go back in with a smaller tool and cut all these corners out. It looks like this. We also, you know, like we talked to the tool path and the roughing, we added a radius in the back. In this one, we add a radius, and we use a routine called driving in the corners, which will not engage this tool any more than what we want to. So instead of jamming itself back in the corner, it'll do a little tricordo in there if it has too much stock, and then get back to the back of the fillet or the corner. It cuts a lot smoother, and it has a lot less engagement of the tool. So the tool lasts a lot longer. It's a lot more consistent on tool life and so on. It's a real good cut. All right, step 3. This is called roughing the low-lying areas. Now that would be horizontally from like 0 to 10%, something like that, on your low-lying areas. And when we're roughing those out, what we're doing is taking the scallops out that the Z-level left in the bottom of the part from 0 to 10 degrees up, and we're just roughing the low-lying areas to get rid of all the cusp and stuff that tool left. So step 3 is called roughing the low-lying areas to get that portion out, and it looks like this. So in this case, we're just doing a raster across the part, and we chose like a 45 degree in order to keep the air cuts to a minimum, because you can go at any attitude, you know, horizontally from 90 degrees to 0 to 180, or you could do like we did and come across this part at 45 degrees. Now step 4 is remachining our corners again. So what we're doing there is, yes, we've remachined the corners, and typically what you're going to have in a large part, unless you have a real small part, in a larger part, like this piece is maybe 10, 12 inches long. So we're going to step those corners down. So the first one that we used, we went, and yes, we did remachine the corners, and now we're going to go with a smaller tool, and at this point we're using a 3mm ball end mill, so we're getting down kind of small. We're going to hit those corners again and drive our corners or our fillets in there a little bit closer with a smaller diameter tool. And that's what we call step 4 of the 7-step process. It's remachining corners again. All right, dynamic machine control. This is basically a 3+2 technology, and it optimizes our attitude that we're going to set that the last 2 axes. So it's a 3-axis, but we also are going to move in a fixed axis an extra 2 axes, and so that we can position this tool in here without having any crashes or interference to the spindle or any of the rotating axes, the tool holder, and the tool itself. And it's very, very easy to run this. It's really quick, and it's super simple. But basically, they'll look at it after they've created their program, and then they'll run this through the technology that they have, dynamic machine control, and they'll go in and it'll show you. And up here in the right in the chart, if you notice, you have all these red marks that's showing you collisions all the way through here. So we know it's got some collisions. We're going to go back in here and just grab it. You can see the little pointer, and it just grabs it and turns it until the red goes away. And then once the red goes away, we're going to rerun it again. We're going to see if we have any more errors. They're going to come up here. They're going to update the tool path. going to go over here, clear out the chart of all the past interferences that it had, and then we're going to rerun it. If we have any red show up here, then we're going to have to change the attitude again. But it's a simple dig and drag to get this thing in the right attitude of the last two axes. So it's a 3+2. It really helps out to make sure that you're not going to have interference with your tool and or tool holder and spindle in the rotating axis, so that you're not going to have any interference crashes or anything like that. It's pretty powerful. All right, this is just showing you in a large graphic in 3+2. So you're looking at just a standard vertical machining center and a piece on there. If you notice these green marks down here, those are areas that need to be machined down. And this is just showing us, you know, where that is. You can see in the light gray here on the left-hand side of the end of these green tool paths. You can see we got an undercut there that we have to get, so we're going to have to rotate this part around. So after we've looked at that part back there and we know it's cleared, that we can change the attitude, we can go in here and bust this part out. We can cycle start and walk away from this machine. And it looks like this. So we're running in 3 axes simultaneous and positioning with the other 2 axes to get in there and remove some more of this stock that's got some undercutting in this part. All right, it's ACA, or automatic collision avoidance. This is a live 5, and we're going to go in here and we've got a little graphic over here on the left, and then the actual part as it's going around. Now this is live 5. What we're saying is we're going around here in a 5-axis simultaneous movement of all 5 axes. This is a simulated view of what that's going to look like. And this is the video of it, that same tool path, and actually doing the cutting. Down around the bottom, 5-axis movements. Everything's great. We don't have to worry about tool holder crashing the sides of this part because we've already done our simulation. Now granted, if you don't have the right geometry in there for your tool holder, you can have some issues. But if you get all your ducks in a row, it's pretty nice to have. Now, chatter in this fillet, how do we get that? The actual chatter that we ran into here is because we had, let's say, an 1/8 inch fillet radius in here, and we had a little disagreement initially between the programmer and us. And he was saying, well, it's got an 1/8 inch radius, we use a 1/4 inch ball end mill and go ahead and semi this fillet out and everything will be great. But the problem is, because it's so engaged in these corners, that you get a lot of chatter, and then once you get that chatter in there, it's pretty hard to get it out, depending on how stout your tool is and the setup and stuff like that, how far it's sticking out and whatnot. So it's desirable not to have this in here. So what you really want to do is have a tool that is smaller than the fillets you're going to be cutting, if possible. All right. Now, on a Micron and other machines, some of the machines that have 1G acceleration, how does that affect your cycle time? It affects your cycle time because it's a lot faster in these little intricate areas. And if you remember early on, I was talking about these straight corners that we had designed in this part. We went back to the design, the CAD department, and they said, yes, you could have a 0.5 millimeter radius in there, so we did that. In those real tight areas, when you have 1G acceleration, it really affects your cycle time a lot. It reduces it a ton. So that's going to help you when you're quoting jobs and looking to reduce your cycle times a lot. All right. This is what it looks like in reality. So it's pretty quick in these little bitty areas here, jumping around. Your standard high-speed machine is not going to get up to those feed rates unless they have something like 1G acceleration. So it's pretty quick. Now, finishing parabolas with a one tool path. What that means is we'll start down at the bottom. We'll do an expanding pocket on that sphere in the bottom, and then just bring this thing all the way up, just rotating this part around. And what that does is it really cuts down on your blends or your matching from one tool to another because of using, you know, different style tools and stuff like that. So we don't have to worry about blend lines and things like that. We're just doing one tool path and bringing this up when we're doing a parabola like this. And this is the way it's going to look. Now when you cycle start that on the bottom, you better have some software that helps you do a simulation on your tool path and make sure you're not going to wreck anything. Because there's a lot of stuff happening right now as this thing comes around. And as it comes up, it'll slow down a little bit. There we go. So we're slowing down a little bit as we're coming up, getting up on the diameter. All right. So how do we do it? That's exactly how we did. We started at the bottom in that sphere, doing a parabola. And as we came up, we used one finished tool path that cuts out all our blends. We're using one 5-axis and one finishing tool path. Basically, your tools are going to wear a lot better coming around here too. So radius accuracy is the key when you're going 5-axis machining. You know, if you think you have a 6 millimeter, 1/4 inch diameter ball end mill, it better be that. Otherwise, it's going to throw you out of tolerancing, and then you're also going to have some issues with blend lines and things like that because it thinks that it's up to size, and if it's not up to size, of course, it's not going to give you what you're looking for. So basically, looking at these finishes as it comes around here, this thing turned out pretty much a perfect part. I'm real happy with it, looking at all the details. So what have we learned? Well, we've learned that using the 7-step process, and these are the 7 steps. I'll just go through them briefly with you. We have the Z-level roughing. Then step number 2, we went in and remachined the corners. So we've remachined in the corner areas. Then we go back and rough the low-lying areas. That was from 0 to 10 degrees on the flat areas. So we rough those out. Then we go back in and we remachine the corners again. Why? Yeah, we remachine the corners again because we go back in these corners that are a little bit smaller, and we use another small tool to get in there. So you know, it might be those tools had to hang out a little bit further, and so we can't machine as fast as we could. So that's why we remachine corners a couple times here, is to go to smaller tools as we go down. So we rough the low-lying areas, then we remachine the corners again with a smaller tool. Then step 5, which you haven't seen, but step 5 is just a semi on the complete part. That's from top down, and typically that's kind of like your Z-level. You'll just step it down. And number 6, step 6, then we finish the part. And then step 7, lastly, we finish in our corners any that we didn't get to, like those 0.5 millimeter diameter tools. We'll go and do those, and then also any flat areas, and we'll do that with either a bullnose style tool or a ball end mill, and we'll do that. So that's a 7-step process. Do we always follow it? No. And like I said, if you think about a salad bowl, would you take that salad bowl and use all 7 steps of the processes on this? No, you wouldn't need to. You just do a rough semi-finish and you're done. But any part that has some detail to it, it's going to help you a lot to follow these processes through. And a lot of people skip step 4, remachining the corners. They skip that area thinking, you know, we'll do that when we finish it. Well, you're not going to get a part that looks great unless you go in there and you remachine those corners and get them down. Main thing you want is, when you finish the part, is you want a uniform thickness of material left for the finish tool. So when you're done semi-ing this part complete and you got all your corners cut out, you want a uniform film. If you think about like saran wrap, lay that across the part. After the last semi, before you finish, you should have a thickness similar to that saran wrap that's over that part, and then you'll get a really, really nice looking part. Now, we used a combination of our 7-step process on this, so we didn't use every single. In other words, there wasn't any flat areas that we did with flat tools and stuff like that. So, but this is basically the way we did it. And to cut that part, being about, I think it's 10 or 12 inches long, and maybe 6 inches across, a couple inches deep, to do it on that machine, it took us 7.5 hours cycle time. Now, a couple thoughts here before I shut this down. Are there 3-axis parts where a 5-axis machine would be better? Sure, but there are parts like this that, yes, we can get to that with a straight vertical machining center. We can get to all of them, and we have long length to diameter ratios, but it's doable. It can be machined. Would it be better on a 5-axis? Yeah, when you're thinking about it, a 5-axis, it would shorten up all those tools. That means we can get a lot more aggressive because they're not hanging out so far, and that'd be a lot better deal. But, you know, typically when you got a 5-axis machine in a shop, it's the machine that's usually filled up, and so you just can't put every single part because it would be the best for that part. You got to go with the flow through the shop, and it's just some thoughts. But yeah, we could do this part on a straight vertical machining center and do a good job. It wouldn't have to be 5-axis. And at this point, I know this is not live, so if you have any questions, you can get a hold of me. My name again is Steve McBride, and you'll find my contact information on the website here. Thanks for attending.